Hello friends, welcome to engineering tutorial. So we'll continue our discussion related to optoelectronics devices and systems. So far we have discussed about the classification of semiconductors, about the atomic structure. In this video we are going to discuss about another very important uh, concept related to semiconductors, particularly from the point of view of optoelectronics uh, devices and systems, and that is the energy band theory of semiconductors. So, in the previous video we discussed that according to Bohr's atomic model, the atom, it consists of a positively charged nucleus around which the electrons, they revolve around in certain well designated orbits having fixed energies associated with them. Okay, each orbit, the electrons in each orbit, they have a fixed amount of energy. So that energy associated with each fixed orbit is called as an energy level. Okay, each orbit has certain fixed energy level associated with it, and as we move away from the nucleus and the number of orbits, it goes on increasing, so does the value or the magnitude of the energy. But in reality, it is not just one value of energy, but a range of values, okay, with a lower end and a higher, the minimum value and a maximum value. Each orbit has a range of energies. Why? Because when we are talking about atoms, they are not isolated. Okay, it consists of many atoms. Okay, a large number of atoms are present in a semiconductor material. So if we are talking about an isolated atom, this energy level diagram is right. Okay, isolated atom, it has fixed values of energy for each orbit. But if we are talking about a material, a semiconductor material with large number of atoms, because of the interatomic interactions, each orbit, it has a range of energies, and it is like this. Okay, orbit 1, it has a range of energy with this the lower end, this the higher end. Similarly, orbit 2, it has a slightly higher range with this the lower end, this the higher end. Okay, let's add subscript 1 here, 2. Similarly, here orbit 3, it has a more higher range. Okay, so here this is the lower end of orbit 3, lower energy, and this is the higher energy. So the energy associated with each orbit, it will be lying in between these two values. Okay, lower and higher value for each orbit. You understand, it is not like this. Okay, it is not fixed energies but range of energies. It will be in between these two values for each orbit. Okay, for orbit 1, it will lie in between L1 and H1. For orbit 2, the energy will be in between L2 and H2. For orbit 3, it will be in between L3 and H3, and so on. Okay, so this is the energy levels in semiconductors. Now, what is the importance of these energy bands in semiconductors? So we are particularly interested in two energy bands. First is the valence band, second is the conduction band. Now, for an atom with the outermost orbit, if we take that into consideration, the outermost orbit, the energy or the range of energies possessed by the outermost orbit electrons, which is called as the valence orbit electrons or valence electrons in the semiconductor, that is called as valence band, the energy possessed by the outermost orbit electrons. And as this orbit is of maximum radius, it is outermost radius, it is So because of maximum radius or maximum distance away from the nucleus, it has the highest energy, as you can see here. Okay, the range of energies, it is high as compared to orbit 1 and 2. This is the valence orbit. This is the valence orbit, orbit 3. It has maximum range of energies as compared to orbit 1 and 2. So that is called as the valence band energy. Next is the conduction band. Okay. Now in some substances, some materials, the outermost electrons, okay, the outermost orbit electrons, they are loosely attached to the orbit. Okay, they are loosely bonded to the nucleus. The affinity is less towards the nucleus. They are loosely attached and they get detached easily and become free electrons. Okay, they become free electrons, and these free electrons are responsible for conductivity of the material, the ease with which current flows through that material, that is decided by these free electrons. So when a number of free electrons, they occupy a certain energy level, when they become free and occupy a certain energy level, the summation of those energies, that total energy, is called as energy of the conduction band or simply conduction band. Okay. So here you have to understand that in order for these outermost electrons, okay, the electrons which are at the outermost orbit, the valence orbit, in order for them to become free or conducting electrons, they have to be, supplied with a certain value of energy. So that energy value, the difference of energy value between the conduction band and valence band, that is called as the forbidden energy gap or energy gap between valence band and conduction band. So here you understand, if we take this figure into consideration, this is the valence band, which is the energy occupied by these outermost electrons of the m orbit, this 4 electrons of the m orbit if we are talking about silicon. So this is the energy occupied by the valence band. Now if we want that these 4 electrons, they become free, they become conducting electrons, they want to occupy the conduction band, they want to become free, we have to supply them with a certain value of energy. For silicon it is 1.1 electron volt, for germanium it is 0.7 electron volt. Please here don't confuse them with the barrier potential. Barrier potential is different, this forbidden energy gap, that is different. Okay, barrier potential is 0.7 volt for silicon, and for germanium it is 0.3 volt. So don't confuse them with that. So here if we want the 4 valence electrons of silicon to become free and conducting electrons, we have to supply them with this much amount of energy, 1.1 electron volt for silicon, 0.7 electron volt for germanium. Then these valence electron, they will move to the conduction band and become free electrons when they are supplied with this much amount of energy, which is called as the energy gap or band gap energy. That. Now what happens for insulators, okay, which have very low amount of conductivity, high resistivity, this energy gap is very high. Almost in all insulators it is greater than 6 electron volt. So only when you are supplied with this high amount of energy, then the insulators, they become conducting. In case of conductors, good conductors, there is no energy gap actually. The conduction band and the valence band, they are overlapping in nature. So that's the reason why without any external energy supply, the good conductors, they start conducting naturally, because there is actually no energy difference, no energy gap between the valence band and conduction band. But semiconductors, they lie in between good conductors and good insulators. Okay, perfect conductors and perfect insulators. In between we have semiconductors. We have where the energy difference is in between these two. Okay, for insulators it is very high, for conductors it is none, for semiconductors it is somewhere in between. Okay, like this. So here this is the energy band diagram of the semiconductors. Okay, so next concept which we have to discuss is the energy levels in isolated atom, and we'll discuss that, the splitting of energy levels, how it happens. So what happens for an isolated atom, we are taking only one atom into consideration. The electrons which are revolving around the nucleus, they have discrete energy values, okay, single energy values, as I was talking of this, okay, here like this. For an isolated atom, fixed energy levels, okay, single definite energy levels, not like this. This is for a combination of atoms, multiple atoms. For an isolated atom, this. So that value of energy is given by this equation as per Bohr's atomic model, taking into account hydrogen atom into reference this. So here that is m0 q4 by 8 epsilon square h square n square, which is equal to minus 13.6 by n square electron volt. So here q is the electronic charge, m0 is the free electron mass, h is Planck's constant, n is the principal quantum number or the orbit number, and epsilon 0 is the permittivity of free space, absolute permittivity. So if you just want to simply remember this, minus 13.6 n square electron volt. So here as you can see, the energy depends on the orbit number. So for the ground state, discrete energy is this, for n equals to 1 minus 13.6. For the first excited state, it is minus 3.4 electron volt, and so on. For higher values of principal quantum number, higher orbit levels, the energy levels, they split according to the azimuthal or angular momentum quantum number. So that is a bit of physical chemistry involved here. So we will not go deep into that. Simple way we'll understand that when we are considering two identical atoms, okay, separated by a large distance, okay, identical atoms, they will have same amount of energy levels, okay, they will have same amount of energy levels. Okay, so let us try to understand. Let us say we have two different atoms, okay, we have two different atoms which are separated by a large distance, okay, they are separated by a large distance. So they are isolated, we are considering isolated atoms, so they will have certain fixed value of energy for a particular orbit, or particular quantum number n. When we bring together these atoms, that is, we reduce the distance, okay, we keep on reducing the distance. In that case, when these atoms are brought together and their distance, it crosses a certain threshold value, what happens, certain minimum distance, these energy levels, fixed energy levels that I am talking about, these fixed energy levels for particular quantum numbers, let us call it E subscript n, energy for a particular quantum number, these energy levels, they split into two parts, okay, this split like that. When the interatomic distance between them, it crosses a certain threshold value, beyond which it splits. Up to this it is constant, okay. This is, let's say, this is the energy and this is the interatomic distance. So when the interatomic distance between two atoms is maximum, it is high, it is single, fixed. But when the interatomic distance, it goes, you know, below certain threshold value, this threshold value, it splits. So that is called as a doubly degenerate level, okay. It is called as doubly degenerate level. So when two identical atoms are brought close together, these doubly degenerate levels will split into two parts, which I was just saying, okay, like this. This is the threshold value of interatomic distance. Now let us say we have n atoms, n identical atoms that are brought close together. In that case, we will have n, you know, splitting of n energy levels, n closely spaced energy levels, like that. So this concept leads to, if we try to understand it in terms of conduction band and valence band for silicon, which has atomic number Z is equal to 14 and the electronic configuration is 1s2, 2s2, 2p6, 3s2, 3p2. For the outer orbit consisting of 4 electrons, 3s2, 3p2. When n atoms of silicon come together, the 3s and 3p subshells, they will interact, overlap and finally split at around the equilibrium interatomic distance, and it will be something like this. So here you see, here we are talking about single lines, okay, thin lines, but here it is drawn in the form of bands. So I said previously that when we are talking about isolated atoms, they will have fixed energy levels which can be represented in the form of lines, fixed. But when we are talking about actual material, semiconductor material or any material, because of their interaction with other atoms, they will occupy a range of energies. So it will be in the form of bands, okay, not lines like this, not like this, okay, not simple lines, but this in the form of bands. So here the topmost portion of the bottom band, that gives us the valence band energy EV, and the bottom most portion of the top band, that gives us the conduction band energy. For 3p, the bottommost portion gives us conduction band. For 3s, the topmost portion gives us the valence band. That's why the 3s to 3p2, the outermost orbit, and these two subshells, they are very important, okay. Again understand, for 3s, the topmost portion or the upper region gives us the valence band energy EV. For 3p subshell, okay, for 3p subshell, the bottommost portion of that band gives us the conduction band energy EC, okay. So this is the valence band and conduction band which we are discussing. Another important aspect which is related to, you know, our understanding of energy band diagram of semiconductors is the energy momentum relationship for the free electrons in the conduction band. So the energy of a free electron which goes to the conduction band after breaking away from the valence band is given by this. E is equal to p square by 2m subscript o, or h square k square by 2m, where p is the momentum of the free electron, m0 is the free electron mass, h is Planck's constant, and k is the wave vector for that electron. So here the electron effective mass is that when an electron is inside a semiconductor material, it experiences forces, internal forces due to the ionic lattices in the crystal. So for that reason, the mass of the electron gets a little bit altered, it gets changed, and that changed mass is called as electron effective mass. Okay, so the energy momentum diagram, it is something like this. It's in the form of a U-shaped curve, okay, where E is the energy and here we have P, which is the momentum. And the same when we try to express it in terms of the wave vector k, it is also the same U-shaped curve like this. So the same can be represented for valence band and conduction band electrons. So it looks something like this. For conduction band, it is a U-shaped curve. For valence band, it is an inverted U, or you can call it a V-shaped curve also, V-shaped, and this is an inverted V-shape, okay, like that. And both of these bands, they are separated by a certain value which is called as the energy gap, forbidden energy gap. So here the peak, the crest and the trough, okay, the maximum point, maxima and minima points of these curves, they also play a very important role in deciding the nature of the semiconductors. So that gives us another concept, another important concept, which is the direct and indirect band gap semiconductors. Okay, so direct and indirect band gap semiconductors. So on the basis of the points where the minima and maxima of the conduction band and valence band coincide, we can classify semiconductors in terms of their band gap as direct and indirect band gap semiconductors. So in direct band gap semiconductors, the conduction band minima and the valence band maxima, they occur at the same momentum value or same wave vector value, okay, same p value or same k value. So like this, here the conduction band minima, the minimum value, and the valence band maximum value, they occur at the same momentum value, p value or k value. Example of that is gallium arsenide, gallium nitride, indium phosphide. This direct band gap semiconductor is of utmost importance in optoelectronics. Most of the optoelectronic components, be it source, the sources or detectors, they are made from direct band gap semiconductors, because the transition of electrons from valence band to conduction band at the same momentum value is easy, comparatively easy, as compared to the indirect band gap semiconductors, which is the opposite, where the conduction band minima and valence band maxima, they do not occur at the same momentum value. Okay, this, they occur at different momentum values. So example of that is silicon and germanium. So here the point which I was trying to make is that for the basic operation of all optoelectronic devices, they are based on the transition of electrons from valence band to conduction band. Okay, here in case of direct band gap semiconductors, this transition is easy at this momentum value, where the conduction band minima and valence band maxima coincide, because the energy gap will be less. But in case of this, here it will cause a change in momentum value from here to here to make that transition. This transition is comparatively difficult. So in most of the cases, you will find direct bandgap semiconductors, compound semiconductors. They are compound semiconductors consisting of multiple semiconductor elements, multiple elements. In case alloy semiconductors are also used. So you will find direct bandgap semiconductors with this nature used in optoelectronic materials. So for that, the understanding of direct and indirect bandgap semiconductors is very important. Okay, so I hope you like this video, and please subscribe my channel Engineering Tutorial for more such videos related to engineering, science and technology. Have a great day. Thank you very much.